In this video, we're going to have a look at the radioactivity part of the IGCSE CIE syllabus. Well, part of it anyway. Now, the part we're going to look at is the detection of radioactivity and some characteristics of the three kinds, so that's alpha, beta and gamma. Also how they interact with electric and magnetic fields. We will, however, not do this part. They explain the practical applications, that's just the uses. So, for example, the fact that gamma is used in radiotherapy. You can just look that up and you just need to learn it. We'll look at radioactive decay, what it means, and some equations relating to that. Start off with, what is a radioactive decay and what is a radioactive emission? Well, there's three types of radiation, alpha, beta, gamma. Don't get confused with infrared radiation, that's completely separate. They're emitted from unstable nuclei, it's something known as a random process. Now let's look at those in a bit more detail. There's alpha. You can see alpha consists of 2 protons, represented by the red, and 2 neutrons. This happens to be the same as a helium nucleus, so sometimes people say it's a helium nuclei being emitted. Why is it just nuclei, not atom? Well, there's no electrons. It's just one of those, and it comes out the nucleus of an unstable atom. The next one is beta, which involves the emission of an electron from the nuclei. We'll see where that electron comes from later, because it might be a bit weird thinking, well, electrons coming out of nuclei, that doesn't make sense, because electrons are in the orbital clouds around the nuclei. The last but not least one is gamma, and this involves an electromagnetic wave of high energy being emitted by a nucleus. So as we mentioned, they come from unstable nuclei, and when this happens, the nuclei changes. It might break apart, and well, it's not really entirely correct, it doesn't really break apart, but it just becomes a bit smaller, or not necessarily smaller. Sometimes we'll see that actually just changes as well. So we'll have a look at that in a bit more detail. Let's start with alpha. So we can see here, if Ra226 decays to Rn, which means radon, by alpha emission, you can see here we represent the alpha with the He42. The 4 is the mass number, so that's the number at the top up here, and the 2 is the atomic number or the proton number. In physics, we often call this the nucleon number and the proton number. As we can see, the numbers at the top, so the 222 and the 4 here, have got to equal the number that we started with. We can't just lose nucleons. So if we start with 226, 222 plus 2 plus 4 gives us 226. Likewise, at the bottom, the 88 has to equal the 2 numbers on the bottom there. Beta is a bit more confusing because we're getting an electron coming out. There it goes, that green thing. Bit weird. Let's see what's going on. Well, with beta emission, we lose a fast-moving electron. And what actually happens, which is a bit weird, but a neutron changes into a proton and an electron. We'll show that a bit more in the next slide. Oh, there we are. The next slide, you see the neutron in the nucleus is a bit unstable. So over time, sometimes it decays into a proton and an electron. The reason why we have to have both, well, the proton's positive, the electron's negative. There's also this weird thing here, which is called an anti-electron neutrino, but you don't need to know that, hence why I'm going to cover it up there. So that's what happens, and we get an electron emitted. If you see down the bottom here, you can see the equation for this. Now, electron has a mass number of 0, because it has no protons and neutrons, and the bottom number is a -1, because it kind of represents the charge. So that means that the 39 plus the -1 has to give us the 38. So we're actually increasing the proton number by doing beta decay, which seems a bit weird. We can actually make an atomic nuclei which has a higher proton number, which is pretty cool. The top number, the nucleon number doesn't change because we're going from a neutron to a proton, and this is just the number of neutrons and protons, so it stays the same. Gamma is the easiest. Well, nothing changes because a wave gets emitted, so a wave just comes flying out, and the gamma nuclei loses a bit of energy, so nothing that exciting there. So just a quick reminder that we represent alpha as either the alpha symbol with a 4 and a 2 or the helium symbol with a 4 and a 2. Beta is the electron, so you can write it as beta like that, that's the symbol for beta, or the electron symbol like that. Gamma, you represent with the gamma symbol, and the great news here is that actually the top number, the bottom number, the mass number, or the nucleon number is the same. It's the same as 0. Sometimes the decays are quite complicated, as you can see here. This is uranium, just thought to show you this. Uranium decaying by alpha emission, and then beta, and slowly working its down to stable lead over here. This happens over millions and millions of years. In fact, I think the half-life for this first bit is about 4 billion years. We'll see what half-life means later. Just interesting up here, look, you can actually go, if you do start with an element like uranium-238, that decays by alpha decay to thorium, then to Pa, and it can actually end up going back to uranium. So if you do an alpha decay, then 2 beta decays, you can actually end up back at the same element, but just with a different nucleon number, which means that it's an isotope. So these two are isotopes of each other. Just one for you to make a note of, the symbols for protons, neutrons, and electrons. Sometimes you need to represent them. Protons are 1, 1. Neutrons are 1, 0. Because remember, that's the number of protons represented there. And electron, as we know, is 0 minus 1. How do we actually detect these alpha, beta, and gamma particles? Well, this is down to good old Geiger Muller tubes. All they are is a device or an instrument that you point at in the direction, and it beeps when it detects some radiation. It's connected up to a counter, which records the total amount. You can also use photographic film. That was used much more in the olden days, but that can detect radiation, or a cloud chamber, which you can look up. Units for radiation are often measured in becquerels, symbol BQ, and that's basically the number of radioactive particles you detect or emitted per second. So 2 becquerels would mean that we're getting 2 radioactive particles per second. Might be alpha, might be beta, might be gamma. We must also make a note that nuclear decay is random. What does that mean? Well, some things we say are random aren't really random. We say, oh, that was random. Well, no, it probably wasn't. This is truly random. It is impossible to predict when an individual nuclei will decay. Over a big group of nuclei, we can get probability of some decaying. That's why we can make predictions, but we can't predict when one individual one's going to decide to decay. They have a certain probability per unit time. Now, actually, radiation happens to be all around us, and this is what we call background radiation. It's natural. You can see a lot of it comes from radon gas from the ground, some from food and drink. For example, bananas are slightly more radioactive. Cosmic rays come from space, and this is why you get a high exposure when you're in a jet plane, because you're higher up, so less of the atmosphere absorbing them. Buildings also emit some, and then there are some that also come from not natural, so artificial sources, mainly medical, and then a small amount from nuclear weapons and power stations. So this is natural radiation that's all around us, and we need to take this into account when we're doing experiments. Now, how are alpha, beta, and gamma different? Well, this table represents the differences here. We've talked about what they are, and we've mentioned their charge as well. Just got to learn that. Here tells you the range. That's how far they go in air. You see that gamma goes on infinite because it's an electromagnetic wave. Penetration tells you what kind of will stop it. So paper would stop alpha. Aluminium, a few millimeters will stop that, beta. And then a few millimeters of lead will reduce it, but won't stop it entirely. You need a lot of lead, and that's why there's a lot of lead used in nuclear power stations and so on. Ionization we'll look at in a bit, but probably in the next video. But you just at this stage you need to know that alpha's high, beta's medium, and gamma's low. Now, why is the ionization level high for a beta particle? We'll talk about a bit more what ionization means, but it's basically the ability for these particles, alpha, beta, and the wave gamma, to knock electrons out, to ionize sometimes DNA or atoms in the process. Well, if a beta particle was a 10-cent coin, had the mass of this, what would be the mass of an alpha particle? Well, maybe have a guess, and you'll be surprised to find perhaps that it's equivalent to 4 bowling balls. So you can see now why alpha is so much more ionizing. It's got a much bigger mass, but it also has twice the charge as well. So when that comes flying towards your cell, it's going to knock some electrons out of the way. This also represents the absorption of alpha, beta, and gamma, which we've talked about. Now, we need to also know the deflection due to an electric field. Well, an electric field might just consist of 2 charged plates, one being positive and one being negative, or we could just have one plate of one charge. Now, we know beta has a charge of -1, so that's why it's attracted upwards there. Gamma is neutral, because it's a wave, so it's unaffected, and alpha is +2. You might be wondering, well, why does beta bend more? Well, that bowling ball analogy earlier might help. Remember, beta is just an electron, so it has very little mass, so very little momentum. Well, it has quite high speed, I suppose, but it still has very little mass and very little momentum, so it's easier to bend that. Whereas alpha has a lot more mass. It's about 8,000 times the amount of an electron. So more mass, more momentum, more difficult to change its motion. So it bends less. So you do need to know that beta bends much more. And if it had less energy, that beta particle, sometimes they have a bit less, they'll bend earlier. Whereas alpha takes longer to change its direction. Now, deflection due to a magnetic field is slightly trickier. You need to again remember the charges for these. Negative there, positive there, and neutral here. So gamma's the easiest. We know that's just going to go straight on. It's unaffected by the magnetic field. You might remember these crosses here mean that the magnetic field is going into the page. And you might remember doing charged particles and the direction they move in using, well, you can use Fleming's left-hand rule for this. But remember that the current finger has to line up with the direction that a positive charge will move in. So alpha is the easiest to do, first of all. Alpha, the current, or the current finger, is the direction a positive charge will move in, and the alpha is moving in that direction. So for alpha, your hand needs to be like this. The magnetic field is going into the page, so this is the mag field. And this tells you the force is to the left. And that's why that force, centripetal force, makes that move in a curved path. Beta, well, you're probably guessing is the opposite because it's got the opposite charge, but you can use Fleming's left-hand rule. This time, remember, you need to line your current finger. That's that one, the second finger. Remember, this is your first finger, this is your thumb. Your current finger needs to be lined up in the opposite direction to the negative charges moving in. And that tells us our force is off to the left. You might want to rewatch that bit because it is a bit tricky to get your head around, or you can memorize it as well. Now, in the next video, I'm going to come and look at these three parts here in a bit more detail and talk a bit more about ionization, because I know we just touched on that, because it relates to how it affects living things. So we'll come back and look at that. Hope you found that video useful. Please let me know if you've got any questions. Thank you.